integrals of exponential functions. At the end of this lesson, you must be able to illustrate step-by-step solutions on integration involving exponential functions. There are two basic formulas for integration of exponential functions. We have the integral of e to the u du to be equal to e to the u plus c, and the integral of a to the u du is equal to a to the u divided by ln of a plus c, on the condition that a is greater than 0 but not equal to 1. Also, in this case, u is a function of x. Okay, let us have some examples. Let's evaluate the integral of y e to the y squared plus 4 dy. In evaluating this integral, we will fit it to the form integral of e to the u du by assigning as our u function y squared plus 4, requiring a differential du of 2y dy, from which the product y dy would just be equal to du divided by 2. So this integral of y e to the y squared plus 4 dy, when written in this form of the integral of e to the y squared plus 4 times y dy, can be shown to equal the integral of 1/2 e to the u du. Remember, we said y squared plus 4 is our u, and y dy is just du over 2. So we now evaluate 1/2 the integral of e to the u du, of which the integral is 1/2 e to the u plus c. But remember, every time you use the u substitution, do not forget to write back the integral in the original variable. So 1/2 of e to the u plus c is now given in terms of 1/2 of e to the y squared plus 4 plus c. For our second example, we have the integral of the square of e to the x plus 1 divided by e to the x dx. In evaluating this integral, what we do is first to expand on the square of e to the x plus 1, so that this integral now will be given in terms of the integral of e to the 2x plus 2e to the x plus 1 divided by e to the x dx. When you divide each of these terms by e to the x, this is what you're going to get. You have the integral of e to the x dx. E to the x is just e to the 2x divided by e to the x. The second term would be given by 2 the integral of dx, and the third term is just the integral of e to the negative x dx. E to the negative x is equivalent to 1 divided by e to the positive x. So that when you evaluate these integrals, fitting it to the form e to the u du, then the integral of the first term is just an e to the x. The second term obviously will just be a positive 2x. The third term is negative e to the negative x plus c. Number 3 example illustrates the use of the integral of a to the u du formula, for which the integral is just equal to a to the u divided by ln of a plus c. In this case, evaluating the integral of 3 to the x minus 3 dx, we fit the integral to the form a to the u, where our a is 3 and u is x minus 3. The differential du will just be equal to dx, and so this integral of 3 to the x minus 3 dx will just equal 3 to the x minus 3 divided by ln of 3 plus c. For number 4, the integral of 5 e to the 4 ln of x dx. The integral of 5 e to the 4 ln of x dx can be simplified or transformed before we evaluate the integral. Remember properties of the logarithm? You have b log of a is equal to log of a to the b, so that 4 ln of x is just equal to ln of x to the 4th, and that this integral of 5 e to the 4 ln of x dx can be written equal to 5 the integral of e to the ln of x to the 4th dx. Okay, and when you have written it in this form, recall these properties of the logarithms, then e to the ln of x to the 4th can just be written equal to x to the 4th. And so the integral is just equal to 5, the integral of x to the 4th dx, for which the integral is given by 5 times x to the 5th over 5 plus c, or simply we have x to the 5th plus c. Summarizing what we have taken up in this lesson, in evaluating integrals involving exponential functions, we have these rules to follow. That the integral of e to the u du is just equal to e to the u plus c, and the integral of a to the u du is equal to a to the u divided by ln of a plus c, provided a is positive, not equal to 1, and that u is a function of x. And that integrals involving exponential functions are simplified using the laws of exponents.